We're used to picturing fundamental particles as rigid, tiny spheres flying through a vacuum, but as they move, they don't hold a strict point shape. They propagate through space as oscillating, localized wave packets. Physicists call these matter waves, or de Broglie waves, named after the physicist who first proposed that moving matter has an inherent wavelength. This diagram illustrates that these waves do not stretch out infinitely in all directions. Instead, they exist as a localized wave packet, traveling together with a specific group velocity that matches the particle's physical speed. This equation links particle and wave properties. The de Broglie wavelength equals Planck's constant, h, divided by the particle's linear momentum, p. This graph proves the mathematical relationship. As linear momentum increases, wavelength shrinks. As it slows, the wave packet stretches out. This provides a direct translation mechanism. To determine the quantum wavelength of any particle in any given environment, we must first determine its classical momentum. In practice, we rarely measure a subatomic particle's exact velocity directly. We usually know its kinetic energy. This breakdown shows how we rewrite the base equation. Momentum, mass times velocity, is substituted with the square root of 2 times mass times kinetic energy. For charged particles, we carry the substitution further, swapping kinetic energy for accelerating potential, v multiplied by charge, q. Because mass and charge are fixed constants for specific fundamental particles, we don't have to recalculate the entire denominator every time. We can pre-calculate these values. These formulas detail the simplified results. For an electron, the math condenses to 12.27 angstroms divided by the square root of voltage. A proton drops to 0.286. The scaling continues for heavier composite particles, 0.202 angstroms for a deuteron and 0.101 for an alpha particle. The logic extends to thermodynamics, asking how heat affects a particle's wavelength. This box shows the result for gas molecules. Substituting momentum using the kinetic theory of gases, we plug in 3, mass, Boltzmann constant, and absolute temperature, yielding the exact wavelength. These derived constants allow physicists to bypass complex quantum calculations. We can map wavelength directly from simple macroscopic inputs, like the voltage dial on a console or the temperature reading on a thermometer. Those formulas calculate static states, but in dynamic environments, a particle's momentum constantly changes over time. Take an electron moving with an initial velocity that suddenly enters an opposing constant electric field. As the field decelerates the particle, its physical wave packet stretches. This top left block defines the baseline state. Initial de Broglie wavelength equals Planck's constant divided by mass times initial velocity. Next, we calculate the classical deceleration caused by the electric field acting on the electron's mass. This deceleration creates a time-dependent velocity function, where current velocity equals initial velocity plus acceleration multiplied by time. We then make the final substitution, plugging this dynamic velocity function back into the denominator of the fundamental de Broglie equation. Following the final algebraic simplification, we arrive at a ratio that relates the exact wavelength at any specific second directly back to the original baseline state. A particle's wavelength is never perfectly static. It's a live variable that breathes, stretching or compressing in real time as it responds to external classical forces. SASTER energetic pace. We can take this logic into multi-body systems, where particles interact with each other without any external fields. These diagrams visualize a one-dimensional spontaneous fission. A heavy parent nucleus, A, splits into 2 equal mass daughter nuclei, B and C, flying off in opposite directions. We do not need to know the specific strong nuclear forces tearing the nucleus apart. We only need the law of conservation of momentum, which must always hold true. This sequence maps the momentum conservation, equating the known initial momentum to the unknown final velocities of B and C. By balancing the equation, we determine that particle B moves out at 4 times the original velocity. By locking in these classical velocities, we instantly deduce the quantum wavelengths of the daughter particles relative to the parent. Conservation laws act as an invisible tether, allowing us to accurately predict the specific quantum states of new particles the exact moment they're born. The math holds its shape even when we escalate the complexity to 2 dimensions, evaluating 2 separate particles colliding at right angles. This problem outlines a perfectly inelastic collision. The particles strike and merge completely. Our task is to calculate the final wavelength of the single resulting particle. It is crucial to note that quantum wavelengths cannot simply be added together like vectors. You can only combine momentum vectors. These vector diagrams show the classical addition. The initial momentum merged to form a single resultant path, marked in red. Because they met at a right angle, basic 2D geometry dictates the outcome. Using the Pythagorean theorem, the final classical momentum squared equals the sum of the initial momenta squared. Next, we replace every instance of momentum with its de Broglie equivalent, Planck's constant divided by wavelength. Through a final algebraic cleanup, we isolate the final combined wavelength. Even in chaotic, multidimensional collisions, the rigid geometry of classical mechanics dictates the exact, elegant geometry of the resulting matter waves. We have calculated exact quantum wave states across thermal environments, decelerating electric fields, and high-speed multi-body collisions. In every single scenario, the de Broglie wavelength behaves as a highly sensitive, dynamic variable that is governed entirely by momentum. Quantum mechanics in these contexts relies on a precise mapping of classical momentum. Momentum acts as the universal adapter. Find the classical momentum, and the quantum wavelength follows.